Good morning, everybody. We'll give just a minute or two here. Looks like we've got a lot of participants joining right now. All right, we'll go ahead and get started here. First, I just want to welcome everybody to the webinar. Say thanks for attending today. My name is Dylan Abel. I am the product manager here at Windrock. I've been at Windrock for about 7 years now. I started right out of school, got a mechanical engineering degree, and then started with Windrock as a online systems engineer. So I've worked in depth with our Platinum Autobalance systems that we're going to go through today. Used to do a lot of the project management and the installs and commissioning, traveling all over the place to work with customers with their online systems. Then I moved into a technical services manager role, worked with our team of analysts, going out and doing analysis jobs for different customers, still working with the online systems team as well, and then most recently moved into our product manager role. You can see there you have an area where you can answer questions. There's a Q&A section. We have also Eric Vest is here with me. He is our field services manager. He's been with Windrock for about 6 years now. He is also highly experienced with the online systems. He's been an analyst, he's been an online systems engineer, and now most recently is our field services manager. So he's here as I'm going through the presentation. If you guys want to ask a question, just go ahead and ask it, and Eric's here to answer those as we keep moving through the presentation. Today we're going to talk about the economic analysis with Platinum Autobalance system on an integral. So we can just take a second here and we'll get this presentation going. All right, today we'll go through the Windrock Platinum system components. We'll go through each of the modules of the Platinum system as well as the Autobalance. We will also go through some site-specific case studies. We'll look at the site background information, the Platinum system that this particular customer purchased, and then 4 or 5 case studies and their economic analysis. So this slide has kind of the basic overview of a Platinum system. We can see this particular one came in a 48 by 48 inch cabinet. It's got a Platinum system controller, 2 input bays, one for the engine side and one for the compressor. It has a Autobalance, a phase conditioner, and a power supply. Now we'll dig into each of these modules separately here in a few minutes, and then it has a HMI on the front of the cabinet. First is a Platinum system controller. This is really the brains of the entire online system. It does all the data collection, the processing, the communications. It has a couple different types of communication paths. It has Ethernet, which we use for the Windrock COM to connect to a computer in the customer's control room to run Windrock MD. It has Modbus RS-45 as well as Modbus TCP. The system controller, you can see on the front of it here, has 2 connections. This is for that Modbus RS-45. On the back side is the Ethernet connection. And then you can see down here, this DB25 is for the HMI. Next is the Platinum phase conditioner. or the encoder module, as some of us call it. It does quite a few things. It's got two inputs, one for your once per turn mag pickup and another input for your degree mag pickup. It also has the three relays. We have a not okay relay. It is for the system itself. It pretty much will change state if there's a problem with the Platinum system itself. It'll let the customer know, hey, our system has some kind of issue. It has become unreliable. The other two relays are for warning and danger. With a single compressor cylinder taking pressures, we end up with about 250 calculations or so per compressor cylinder. We can set high and low alarms or warnings on any of those trend points. You can see on front of the encoder module also, this is to hook up a timing light. Next is the power supply. It's pretty straightforward. It converts 24 volts DC from the field power into the appropriate power that each module needs at a given point in time. It monitors the quality and quantity of the power delivered to each module. For some customers, they require redundancy in their power supplies. If that's needed, we can do that. We can install two of these power supplies into a cabinet, as well as two of the converters as well for redundancy. Last is the Platinum Bay. A bay comes with up to 16 channels. Each channel can be configured for any kind of sensor. So it can be configured for an accelerometer, a prox probe, an engine pressure sensor, a compressor pressure sensor, different kinds of 4 to 20 milliamp process sensors, temperature sensors. We can have up to 4 bays in a cabinet for a total of 64 channels. Last is that Platinum HMI that we saw on the front of the cabinet. HMI it's touch screen. It is configured. Through the Platinum system. It displays live data and live curves. It becomes really useful during troubleshooting and startups and shutdowns. Then we have our Autobalance. The Autobalance collects peak firing pressures from the Platinum system, and it processes those pressures, and it runs an algorithm to adjust fuel valves as needed to keep the engine in equilibrium. A single Autobalance can support up to 10 fuel valves. We can have 2 Autobalances per system to go up to a V20 engine. The Autobalances, whenever you have 2 of them, one is a master and one's a slave, and they're just daisy chained together. Windrock does hold a patent for the Autobalance, as well as some of our other part calculations. So a little background information on the site. It's a Roberts Ranch gas plant out in the Midland, Odessa area. It was built in the 1950s, and then it was actually acquired by Oxy in 1982, and then Duke Energy Field Services, which is now known as DCP Midstream, acquired the plant in 1998. The plant was actually shut down in 2005, and then in 2010, after complete overhauls of these 3 engines that we'll be looking at today, 11, 12, and 13, they included lean burn modifications with the jet cells. The Autobalance systems were installed in December 2015 and January 2016. Units, so as we mentioned, there's 3 machines at this site. 3 of those large integrals. Unit 11 and 12 are Cooper Bessemer GMV H10s with 4 compressor throws. 200 horsepower or 2,000 horsepower machines built in 1967. First and second stage are propane and 2 cylinders for residue. Unit 13 is a GMVH 8. It has 4 compressor throws as well, 1,600 horsepower. It's just single stage residue. So this is just a picture of one of the engines there. You can see the 4 compressor throws there coming off the side. They go and connect up to the engine. So this is kind of the side internal view of a GmbH of an integral. You can see there's one crankshaft that supports the engine power cylinders as well as the compressor cylinder. It's important to note that the GmbH has articulated rods. This complicates the geometry settings that are used for the analysis and the calculations. The articulated rods shorten the overall length of the crankshaft. So this is the picture we saw earlier in the presentation. This is the actual cabinet they purchased. Kind of just go through these high level one more time. We've got a system controller. It is doing all the communication, all the calculations. They've got one bay that is for the engine. So all the pressure transducers that are installed into the engine power cylinders are hooked into this engine bay. We have a compressor bay down here where we have our head end and crank end pressure sensors, as well as crosshead accelerometers and inboard and outboard frame accelerometers. A phase conditioner that has the once per turn mag pickup as well as a degree mag pickup. This particular customer is using all 3 relays, the not okay, warning, and danger. And then of course we have our power supply down at the bottom. And we have our Autobalance that has either the 8 or 10 fuel valves hooked into it. With every project, we do create kind of a high-level drawing package. This is just going through the compressor bay. So as we're talking about, we have our head end and crank end pressures that are installed. Head end crank end pressure sensors. We have our accelerometer over the crosshead. We have that for each compressor cylinder, and then we have 2 frame accelerometers opposing frame accelerometers. Likewise, we have a drawing for the engine side. Here is a picture of a dual port Keeney valve that's been installed with a engine pressure sensor coming off that then goes into the conduit. You can see we also include a heat sink between the Keeney valve and the pressure sensor to help dissipate some of that heat from the engine. To help with our pressure readings and the longevity of the sensor itself. You can see we have our engine bay where we hook in each power cylinder has its own pressure sensor so we can get the peak firing pressure for each cylinder. Then we have a drawing for the Autobalance. Same thing, each power cylinder has its own fuel valve installed. It's important to note that no modifications were made to the fuel system or the jet cells. You can see here, this is the Windrock Autobalance fuel valve that's been installed. This fuel valve takes place of the manual valve that was here. So the customer brought our fuel valve straight off of the fuel header and then ran this hard piping into the power cylinder. So now we'll kind of move into a few case studies here. I think I've got 5 of them to share. Some of them are on the compressor, some of them are on the engine. So case study number 1, starting off with a flow balance trend plot here. I'm sure as many of you know, a perfect flow balance would be 1. Higher than 1 typically suggests a suction valve leak, and lower than 1 typically suggests a discharge valve leak. We can see here that cylinder 1 crank-in flow balance began leaking on about 5:20. You can see it slowly rising here over a few days. Windrock also has our leak index calculation that we also trend over time. This is a proprietary Windrock calculation. We can see that with the flow balance rising, the leak index also started to rise. You can see here, this is where the customer had a warning alarm set at 25. On 5/24, so here you can see where there's no data, this is where the customer shut the machine down. They verified the leaking valve. They replaced the valve during an operational shutdown. Leak index and flow balance both went back to normal after replacement. You can see that it comes back down to normal over here. So these next few slides here kind of go through the leak index as well as bringing up the PVs. So we can see on this particular slide, everything's normal. Our leak index is low. We're calling good condition on both the head end and crank end, as well as our PVs, our actuals and theoreticals are lining up pretty nicely. As we move forward in time, where we have the actual leak being called out, we can see that on the crank end, the compressor, it's calling for a suction and packing leak. We can see that our theoreticals and actuals are starting to spread apart. Then after the shutdown, of course, we can see everything's back to good condition. Actuals and theoreticals are lining up. Our leak index has gone back down. This slide we can actually play. So I'm going to hit the play button. We'll kind of go from no leak. We'll see the PVs kind of spread apart during the leak progression. Then you'll see a skip from the leak progression to where it's back to normal. So here's where you can see that cylinder start to leak. You can see our actuals and theoreticals spread it apart. Now they're back to normal. Within Windrock MD, we have our economics report that we have. This is showing the report from 2 different time periods. One with the leak. Unit cost was about $29.32 per the million standard cubic feet. After the valve was repaired, it dropped down to $28.71, or an operating cost savings of 2%, which is approximately $4,000 per year. This report is a great one to have. It's good for helping you calculate savings cost from a valve replacement so that you can show your boss. So conclusion of this first case study here, it was on unit 13, suction valve leak. was on cylinder 1 crank-in. It began on 520 based on flow balance and leak index. Based on limited experience, the station set a warning at 25 for the leak index as the point at which the leaking valve could be confirmed with valve cap temperature measurements. The valve was replaced during the shutdown. Everything went back to normal. Moving on to case study number 2. This one is on the engine side. So here we can see that power cylinder number 1 on the right bank is trending much lower than the others with compression pressure. So platinum trends compression pressure for each power cylinder. The higher than average compression pressure for cylinder 3L is due to incorrect head being installed. So this is 3L. It's due to that incorrect head. It's got a smaller clearance. So the customer knew that this one would be higher than the other power cylinders. So the one in concern is this power cylinder 1R that is trending lower. So the issue here was blown head gasket. We can see that once the head gasket was replaced, it came right up and fell in line with the other power cylinders here. This is just a picture of the engine power curves. We can see during the bad head gasket, we can see that one actually has lower compression pressure. And then after it was replaced, it fell in line with the other power cylinders. In conclusion, compression pressure on power cylinder 1R was lower than average. Replace the cylinder head gasket during the shutdown. Then one thing to comment on is just that mismatched cylinder head. Moving on, case study number 3 here. This is an interesting one. This is a peak firing pressure trend plot. You can see there warnings and alarms that are set. Warnings are yellow, the alarm is red up here. We can see that all of a sudden this one cylinder here all of a sudden just dropped. Its peak firing pressure dropped lower. It actually dropped down to compression pressure. So the peak firing pressure for cylinder 4R dropped to compression pressure. The operator actually got an alarm, went out to inspect the unit. Once he got out there, he found out it was a jet cell plug wire. So he reconnected that wire, which caused the peak firing pressure to rise higher than normal. This is because the autobalance had been opening the valve while the pressure was low. So whenever this pressure dropped down here, the autobalance valve actually started opening up, giving that power cylinder more gas. So then once the wire was connected again, it had more gas than the other cylinders, which caused a spike in the pressure. And then the autobalance reacted once again and started pinching off or closing that valve, bringing that pressure back down to normal. And you can see it falls in line. This is just a picture of the power curves for engine kind of before and after. You can see that here's that cylinder whenever it fell down to compression pressure. And then here it is after it's fixed. You can see that the autobalance is doing quite a nice job on this engine, keeping it balanced. Everything's stacked on top of each other. The engine uses a rich mixture in the jet cell to ignite a lean mixture in the cylinder, which in return reduces emissions. Important to note that the spark plug itself was not enough to ignite the gas mixture in the cylinder. So this is the fuel consumption during that time period. You can see that it's slowly rising over time throughout this 2 days here. So this is rising because whenever that peak firing pressure dropped down to compression pressure, the autobalance opened up that valve. So that would cause the fuel consumption to increase in this scenario. There'd be a sharp rise in fuel consumption during the event that would have continued without the online system. So just to kind of recap, the wire was reconnected here, and then that, since the autobalance had opened up so much given that power cylinder fuel, the pressure shot up, and then the autobalance quickly adjusted the fuel valve. Just conclusion, reconnected jet cell plug wire on 4R. Low peak firing pressure on cylinder 4R generated warning alarms. The operator went out to the engine to investigate, found the plug wire was disconnected, and quickly reconnected that wire. Another case study here, number 4. The Platinum system calculates some statistics for us. So it calculates percent poor combustion, good combustion, overpressure, pre-combustion statistics. These are relatively new features in the Platinum. We can see here that cylinder 3L is getting worse over time. You can kind of see it spiking up here. And especially over here, you see it spikes up and it kind of stays up for a little while. So this is trend plot of the peak firing angle standard deviation. You can see before the fix, it's much higher than the rest. And then after the fix, it's down here mixed in with the others. The increase in the standard deviation for this cylinder pretty much tells us that the peak firing angle is moving more and more. The standard deviation of the peak firing angle of cylinder 3L is also higher than the other cylinders. This indicates that the peak firing angle is moving back and forth during the 30 cycle average. This is the pressure curves for that cylinder with our stats box brought up. The stats box is useful in that it'll give you the standard deviations of the pressure on the y-axis, and then standard deviations of the angle on the x-axis. So here we can see that we are moving around quite a bit in our angle and our pressure. After it was fixed, you can see how tight that stats box gets. This is a picture of a GMVH jet cell. It's important to note that the incoming fuel supply, the check valve, rich mixture, lean mixture in the port. As the piston's moves down towards BDC, the check valve will open and release fuel. Then as the piston moves up towards TDC, it compresses the air and fuel mixture in the cylinder. Once the pressure is high enough, the valve will close. The port has been specifically designed to help move the flame front through the cylinder to ignite that lean mixture. So the combustion chamber is shown as, I believe it is number 12 here on the drawing. Important to note that. So this was the problem, was the jet cell with this particular case study. You can see the jet cell that was removed has some erosion there around the port that causes the cell not to release a good flame front, which in return causes the poor combustion. So you can see the difference between the one that was removed and then the new one there in the photographs of the orifice opening on the old jet cell and the replacement. So this is a trend of the autobalance valve position. It's important to note this area. This is when it was shut down, where it's flatlined here. The autobalance valve's not moving while the engine's shut down. This is where they replaced the jet cell. Once the unit was started up, the system got good peak firing pressure, so the autobalance right here began to close that valve down. After restarting the unit following the replacement of the jet cell, autobalance adjusted that cylinder to compensate for the improved combustion. So conclusion of this case study, replace jet cell cartridge on cylinder 3L during the outage. This was easily identified with the percent poor combustions increasing over time. Case study number 5, this is the last case study here. Once again, starting off with flow balance trend. We remember the higher than 1 is typically a suction valve, suction leak. Lower than 1 is typically a discharge leak. Unit 13 monitoring system was commissioned in February 2016, showed suction leak on cylinder 383 head-in from the beginning. The system was installed, we started up, right off the bat we saw a leak. The valve was replaced in February. Once again, we've got our leak index. It is from startup, it was trending higher than the rest of the cylinders. This next here we have our PV curves. We have our before and after. You can see the significant difference there after the suction valve replacement. This trend is for our head-in capacity of that cylinder. You can see that as the valve was leaking, our head-in capacity started to increase over time. It went from 2.3 million standard cubic feet per day to about 2.7, which correlates to about 17%. In conclusion, on this particular case study, replace suction valve on cylinder 3 head end. So now we get into some of the economic justifications that the customer gave us. These numbers are from the customer. They're actually from DCP. We are partnered with them on this project. So their capital cost was about $275K per engine. The payback from the engine protection, lower maintenance costs, longer overhaul intervals. So they calculated less than a 1-year payback period, about approximately 7 months. I will mention we've had this project started back in 2016. We've had some other customers since then that have come back and told us that these numbers are pretty close to matching theirs as far as the payback period. Important to note that the capital cost includes the entire project. So that includes the Windrock system, the hardware from Windrock, as well as Windrock's installation part of it, and the subcontractor that installed junction boxes, installed the cabinets, ran the wires, all of that. Some other benefits they got from this system, 10 to 15% fuel savings, lower excess emissions due to fewer unplanned outages, higher detonation margins. The higher detonation margins refers to detonation within the power cylinders that are results from changes in their BTU content. Longer spark plug life, lower mechanic, EA, and operator labor hours. Before they had the auto balance system, they were doing manual balancing. So they had an analyst that would go out there with an analyzer. He'd collect peak firing pressures, tweak the manual valves, open or close, take another round of pressures, tweak the valves, do that all day until the engine was finally balanced. So the auto balance does that continuously. Another item to mention, backing up to lower excess emissions, the excess refers to times when the unit trips, they have to flare off any gas that's in the system. So with our system now up and running, they have fewer trips that causes that excess flare. A couple cool things the customer did with the system as far as integrating it with their DCS. They installed this huge TV or HMI, and you can see they've got all three machines there, 11, 12, and 13 auto balance pages brought up. You can actually see all three are pretty nicely balanced within plus or minus 5% of the engine average peak firing pressure. The operators now have a lot more data that's available to them. It's updating real time. They can see their engine balance, their compressor rod loads, crosshead vibration, frame vibration. They did put shutdowns on high peak firing pressures and then high vibration levels. So if peak firing pressure or vibration level goes above the set danger alarm, we will send a signal to their DCS and it will shut down the machine. Kind of just in conclusion here of all these case studies, Roberts Ranch is successfully using the Platinum Auto Balance system to balance and diagnose their engine issues. When installing the Platinum Auto Balance, it's just important to note that they didn't have to modify their fuel systems or jet cells. And great for them, the economics show that the payback period was actually less than a year. It's about 6 or 7 months from all the different issues that the system found, the lower fuel savings, the emissions, all of that added into that 6 or 7 months. So that is the end of the presentation. I believe we still have a few minutes here. There's a couple of questions Eric's given me here. Okay, so
I think it's right.
Okay, looks like somebody's wanting to go back to slide 43. Let's see here. Which slide is it? Slide on standard deviation of peak firing pressure. Is it this one, Eric? Slide 40?
Yeah, maybe 40.
So we have standard deviation here of the peak firing angle. So here we have the 3L before, which is the gray trace, is higher than the rest. You can see it's kind of just spiking up over time, especially over here at the end, showing us that that angle is moving around. After it was fixed, the gray trace is actually mixed into the data here. This other one that's kind of rose up is the black trace. It's a different power cylinder. I probably should have noted that earlier on. That's my apologies there. So the gray trace actually was fixed, but at the same time, this other cylinder started having a rise in its peak firing angle. And then once again, here's kind of the before and after of that power cylinder. Are there any other questions, Eric? Okay, so there's a question here. It's asking specifically what modifications would be required for one of these systems. So For the Platinum Autobalance system on the engine side, the requirements pretty much are for each power cylinder, we need to install a dual port Keeney valve, which will have a pressure sensor, an engine pressure sensor installed into it. And then the manual fuel valves have to be replaced with the Windrock Autobalance fuel valves. So for each power cylinder, you have a Keeney valve with pressure sensor and a fuel valve. Typically, most customers will run conduit above the power cylinders and have a conduit box at each power cylinder that then the fuel valve and pressure transducer cables will go into that conduit box, and then inside that conduit will be wiring that goes from our cables back to the cabinet. So on the engine, fuel valve, pressure transducer with the Keeney valve, and then of course the cabinet has to be installed. On the compressor side, we actually offer junction boxes that you put in between the compressor cylinders. So there's junction boxes that need to be installed, as well as the Keeney valves for the head end and crank end pressure, and those pressure sensors into the Keeney valves. And then for the crosshead vibration, the accelerometers are pretty quick installed. It's just a quick spot face drill and tap for the accelerometers over the crosshead.
And then we have a question here about if the autobalance system does not require as many labor hours, does an analyst ever need to physically come out to take data site?
Come out to take data.
Yeah.
So I think, so the question was, if the autobalance, is doing the continuous balancing, then does the analyst still need to go out to the site to collect data? I think that's probably a question that's going to depend on the company and their processes. So currently, for this example we went through today, with the Windrock system, it's balancing the engine. It is taking the head and crank end pressures and the crosshead vibration. But we're not doing full monitoring. So there's still, you could have a proximity probe for rod drop, rod run out. We could take ultrasonic data around the valves on both the engine and compressor. There's spark data that can be taken on the engine side. So there's still some items that are not, collected by the online system. But what this does for the analyst is it reduces his workload. So instead of that time that he's spending around the engine, which also brings up another safety concern, instead of spending time on the engine, he now has time to, where he spent a day taking data on 3 machines, he now can spend that day actually looking at the live data to get deeper insights. Any other questions?
Yeah, I've got a couple here I'm working down through. Someone's asked if there's a redundancy for transducers, vibration sensors, etc. As a malfunction of vibration sensor may lead to false alarm trippings. Furthermore, what is the approximate downtime required for modification? Would Windrock installation commissioning services be required?
Mm-hmm. Okay, so the first question was for redundancy of the accelerometers. So as I was going through the Platinum system, each bay has 16 channels, so we could install redundant accelerometers in any of those places and run the wires back to the bay. So that can be done. The second question was, would Windrock installation and commissioning services be required? Yes, for a Platinum system, it's not configured until the very end of the project. So as far as installing so a project can go kind of 2 different ways. One would be Windrock takes over the entire project. So we'll ship you the hardware. We can do a turnkey. We'll we have different companies we work with. We can get subcontractor on site, project manage them. They will take care of running the conduit, installing all the hardware, and then at the very end, they'll give us a call and we'll send an online engineer on site to configure the system and be there during the startup and make any tweaks that need to be done. And also that online system engineer will verify the data, make sure we're getting good, trusted data. The other scenario would be more of the customer owns the project. So we send the customer all the hardware, and then that customer takes it upon themselves, whether they use guys internally or they subcontract it out themselves to run the conduit, install the cabinets, take care of the installation. But then still at the very end, we still need somebody from Windrock to come on site for a day or two for that initial startup and configuration.
I've had a question here about can the Platinum system be installed on an Ajax compressor?
On an Ajax?
On Ajax, which should be able to do that with no issue.
Yeah. So just to make sure y'all can hear. Question was, can we use Platinum system on an Ajax compressor? And the answer to that is yes. We can install it on an Ajax.
We also have, are there any published references or testimonials?
Yeah, so as far as published testimonials, we do have those. We have them on our website, actually. We have, I would say, probably 10 or more testimonials from different customers that have used the Autobalance system, claiming, helped them with emissions, fuel consumption, all of that stuff. Yeah, so there are competitors. I would say that the Dresser-Rand HPFI, the high pressure fuel injection, is definitely a competitor. I think one of our big strengths over that, from what we've heard, to do the HPFI on an engine typically is about $1 million project, whereas the Windrock Autobalance is closer to 200 to 250 per project, depending on how big your engine is. We do have one customer who actually has two 20 cylinders engines right beside each other in the same building. They have the HPFI on one of them, and they have the Windrock Autobalance on the other. They have told us that they prefer the Windrock Autobalance. It's more intuitive, it's more robust, easier to work on, and they have actually moved forward with installing more Windrock Autobalance system as opposed to the HPFI. Yeah, so as far as maintenance for the system, there's not a whole lot. The engine compressors, or the engine pressure sensors have probably an 8 years or higher lifespan. We hardly ever see any of the engine pressure sensors fail. Same with the accelerometers. The compressor pressure sensors require some recalibration. We suggest recalibrating pressure sensors every 6 months on average. That's just simply going into the software, looking at the current pressures compared to what the system's getting and tweaking the calibrations. A 4-throw compressor could be calibrated in 20-30 minutes. It doesn't take very long. The fuel valves have a long life as well if the engine stays healthy. Now, if there's detonation and say the flame front goes back through the piping and burns up the fuel valve, which we've seen a couple of times, obviously then you have to change out a fuel valve. But if the engine stays healthy, you're using the system correctly as it's identifying issues, you're fixing them, then the chances of that happening are fairly low. Other than that, it's really just during your kind of routine maintenance for the engine or compressor itself. We suggest opening up junction boxes, checking the wires, making sure there's any, water leaking in or something like that, making sure all the terminal block connections are good and tight, just kind of general maintenance that we'd suggest once or twice a year. Okay. Okay. Mm-hmm. Okay. Yeah, so as far as modifications, we kind of covered that with the different Keeney valves after being installed. Probably the biggest modification is installing the fuel valve on the power cylinder. That's done a little differently for every engine. Like I said, we've got subcontractors that can come in and take care of that, or customer could do it themselves. So for after sales services, we do have different what we call care programs or extended service plans that we offer, different tiers from basic, preferred to premium. Those pretty much cover items such as you get software and firmware updates as they're released. We release a couple every year for both the hardware plus Windrock MD, which is the analysis software, plus Windrock Enterprise. It includes, if there is, say, a hardware failure, it includes customer support, it includes loaner equipment. So if, say, a pressure sensor fails, instead of sending it to us repairing it, send it back, we'll send you a loaner one or a new one for you to install, then send us yours back. Priority shipping, priority repair. As you get into the higher tiers, we start getting into system tune-ups where we'll come on site twice a year to pretty much upgrade software, upgrade firmware, do sensor calibrations, check all the wiring, replace any parts that have failed or malfunctioned. We get into system tune-ups. We even get into monthly data reports where you can zip up your data, send it to us through our portal. We'll do a report on that month's data. So you zip up 30 days, send it to us. We send you a report back within 2 to 3 days, typically, if not faster. So we do offer kind of some aftermarket, after-sale services. Do we have any auto balances currently installed in Pakistan area or the Middle East? I can't think of any off the top of my head. I would have to, we could dig through some of our project files and see. I can't think of any off the top of my head. We do have some of our online systems installed. If I remember correctly, there's actually a plant in Bahrain that has a few of them. We have some that are offshore on a rig in the Caspian Sea off the coast of Baku. Any other? I think we got, looks like we got about 5 or 6 minutes here. Probably fit in another question or two if anybody has one. So question is it possible to share the technical proposal and detailed site survey report during the project? So yeah, during the project's scope, we have kind of, as I mentioned, the different drawing packages. We can come on site and do a site survey, kind of an engine walk down, if you want to call it that, with the customer, subcontractors, everybody that needs to be involved. We can do site surveys, show you exactly where item sensors, junction boxes need to be installed and how they should be installed. we'll share those drawing packages so you can see the high level of the engine and where sensors are going to be installed, all the wiring diagrams, schematics, all of that. We can combine all that in a technical proposal. It looks like we're reaching the end of our time here.
Do we offer would you offer own responsibility, any warranty, guarantee numbers as a success?
So as far as the warranty part of that question, all the hardware, sensors, cables, modules, cabinets, everything that comes from Windrock has a 1-year warranty. If any of it fails, we replace it free of charge. It's got a full 1-year warranty. We have in the past done projects where we will go out and collect data beforehand. We'll even get their customers' emissions data, and we'll do before and after comparisons to look at percent increases or efficiency optimization increases based on the project.
I mean, they're looking at, so they mean the success of the system, i.e. the system will optimize to XYZ percentage, etc.
Yeah. And that's so the question was the system will optimize to X percentage. So we have done that in the past. We had a customer pretty much gave us their emissions data and their current balance data, peak firing pressure balance data of what they were doing themselves. And we told them we could increase the balance from, I don't remember where they were at, but we told them we could take it to within plus or minus 5% of the engine average. And then as well as we could help increase their emissions efficiencies as well. All right, well, looks like we are at the end of our hour here. I just want to thank everybody for joining the webinar. I think this was kind of a good just learning session. I enjoyed being able to give the webinar here and do some teaching. I'm sure we're going to have some more webinars in the future, maybe one a month or one a quarter that you guys can be on the lookout for. If you have time, all the Platinum Autobalance, all of that is up on our website. You can visit the website, look at the product brochures, as well as reach out to Windrock, give us a call, shoot us an email. I'll be happy to get on a call with anybody and do a deep dive into the system if needed. Yeah, so the last question here, how to get in touch with us for more info. Go to the Windrock website, windrock.com. Give us a phone call at the main office. As I said, my name is Dylan Abel. Main office number is 865-330. And actually, I'll give you my number. It's 1117. So just give us a call, shoot us an email, visit website, and we'll be glad to get in touch with you for any questions about the systems. I appreciate everybody's time and have a good day. Thank you.